Welcome to a screencast on an introduction to chemical reaction stoichiometry. Well, first of all, what is stoichiometry? It's the part or aspect of chemistry that deals with quantitative relationships between the substances involved in a chemical reaction. So in other words, it is the part of chemistry that deals with how much of this reactant is needed to react with how much of that reactant, how much of a certain product can be produced, and so on. An example here is the space shuttle or a rocket often uses something like hydrogen as its fuel, reacts with oxygen, and we have representations of the molecules involved in the reaction, what you start with and what you make, and the reaction itself. And the stoichiometric relationships, we'd say, are that two molecules of hydrogen gas react with one molecule of oxygen gas to make two molecules of water. And then, since we typically don't count molecules, we would have to deal with quantities in terms of masses or some other quantity that we could measure very well. So that's what stoichiometry is, dealing with these quantitative relationships. So let's start with an example. Several parts to this one. We have the reaction of iron 3 oxide with carbon monoxide to make iron and carbon dioxide. So this is the reduction of iron 3 oxide to iron. And carbon monoxide is what allows this to happen. And we have three parts to this question. How much carbon monoxide is needed to completely react with a given amount of iron oxide? How much iron could we produce by the complete reaction of a different amount of iron oxide? And then if we actually produce a specific amount of iron from that original iron oxide, what's our percent yield of iron? So let's deal with these one at a time, starting with how much CO is required to completely react with 3.067 moles of Fe2O3. Well, in order to do this, we need to have a chemical reaction and it needs to be balanced. So notice this reaction isn't balanced. Shouldn't be too hard to do. That's something you should probably know how to do at this point. And there is the balanced chemical equation, which we now need. And note, what it tells us is that one Fe2O3 unit reacts with 3 CO units to make 2 Fe units and 3 CO2 units. So those are the stoichiometric relationships within this reaction. The Fe2O3 are formula units of an iron oxide ionic compound. CO, the units are molecules. Fe, the units are atoms. And CO2, the units are molecules. Now note, of course, the relationship is 1 to 3 to 2 to 3 on the basis of units. And if we scale it up to a unit of moles, then the relationship still holds. And that's the key to chemical stoichiometry. This reaction tells us that 1 mole of Fe2O3 reacts with 3 moles of CO, produces 2 moles of Fe, and produces 3 moles of CO2. And all chemical reactions, the stoichiometric relationships are in terms of moles. That's typically what we're going to use. So this is going to essentially just be a conversion problem. We have 3.067 moles of Fe2O3. We need to convert it into, or determine how much CO is required. And what we know is that for every 1 mole of Fe2O3 that reacts, we know that 3 moles of CO are needed. And so if we set up a conversion factor like we've done before, but with moles of Fe2O3 on the bottom, which we want to cancel out, and moles of CO on the top, which we want to get, then we simply do the math. 3.067 times 3 is 9.201 moles of CO, and that is a perfectly acceptable how much. We can have amounts in terms of moles. Now, very often you will want amounts in terms of grams. So if we wanted to continue, we could easily convert to grams, but this is a perfectly good answer to the question. 9.201 moles of carbon monoxide are needed. If we want to convert from moles to grams, that's something you should know how to do at this point. use the periodic table, determine the molar mass of carbon monoxide, 28.01 grams per mole, and then convert from moles of carbon monoxide to grams of carbon monoxide, and in this case the answer is 257.7 grams of CO. Okay, now what we just did is at the heart of stoichiometry calculations in general. Let's do a somewhat more challenging one next. How much iron could be produced by the complete reaction of 247.36 grams of Fe2O3? And here, let's get the how much iron in terms of an actual mass. So we're going to really be looking for how many grams of iron could be produced. Okay, well, a couple things we're going to need to know. A mole of Fe2O3 is 159.688 grams. Use the periodic table and determine that. And the reason we want that is because we need to get the iron 3 oxide converted from grams to moles, because the reaction happens on the basis of moles. This doesn't tell us how many grams of this react with how many grams of that. It tells us moles. So 247.36 grams of Fe2O3, convert from grams to moles. This is something that should be familiar to you at this point. Set up your conversion factor, and that is 1.5490 moles of Fe2O3. That's equivalent to the grams of Fe2O3 that was given. Now next we note that for the Fe2O3, 1 mole of Fe2O3 requires 3 moles of CO, produces 2 moles of Fe and 3 moles of CO2. So if what we want is moles of Fe, now our conversion factor is 2 moles of Fe produced per every 1 mole of Fe2O3 that reacts. We set up our conversion to cancel out the moles of Fe2O3 that we started with to get us moles of Fe, which is what we want, and that turns out to be 3.0980 moles of Fe. And if the question truly was just how much iron could be produced, we could stop here because this is a perfectly good amount of iron. But I did say that we're going to want the amount of iron in terms of grams, so we'll continue and do the last step. 3.0980 moles of Fe. 1 mole of Fe is 55.845 grams, and when we do that calculation, we get 173.01 grams of Fe that could be produced by the complete reaction of the 247.36 grams of Fe2O3. Okay, now note what we did in this problem is going to be the same as we do in general. We have a known amount of some substance. In this case, it was Fe2O3, and we could know it in grams or in moles. We want to get to a known amount or an equivalent amount of a different substance, which we could know in moles or grams, and we have to go through the equation when we convert from moles of one thing to moles of another. And then we use molar mass to go from grams of one thing to moles, or from moles to grams. So we're going to have several conversions potentially, always goes through the equation, possibly involves molar masses as well. Now the last part of this problem is, what if we actually produce 146.82 grams of iron? What's our percent yield? And notice this amount of iron that was actually produced is less than what we calculated in the previous part for the amount that could potentially have been produced. That part, the amount that could potentially be produced, is what's called our theoretical yield, and that's the amount that you would get if all of the substances react as fully as possible. In general, that's not what happens, and so we normally end up having a percent yield, which is our actual yield divided by our theoretical yield, or our what we would potentially get if everything was perfect yield, and then we multiply by 100% to get percent. So in our case, our values are 146.82 grams for the actual yield, 173.01 grams for the theoretical yield, divide those and multiply by 100, and we get 84.862% for our actual yield, or our percent yield. So our last example for this screencast is a reaction between zinc and hydrochloric acid, and we're asked how much hydrochloric acid is needed to completely react with a given amount of zinc. Notice there's something a little different here. We're determining the volume of a 3 molar hydrochloric acid solution. So this is going to be similar to previous calculations, but there will be the difference of, instead of using a grams and moles calculation or conversion, we'll be using a volume and molarity conversion. So we start with what we have, 25.548 grams of zinc. We need to convert that to moles, and 1 mole of zinc is 65.39 grams. And then from the stoichiometry of the reaction, we know that for every 1 mole of zinc, it requires 2 moles of HCl. And then we're going to have to use our molarity to convert from moles of HCl to liters of HCl solution. And we know that there's 3 moles of HCl in 1 liter of solution. And so we string the calculations one after another. Grams of zinc cancels, moles of zinc cancels, moles of HCl cancels, leaves us with liters of HCl solution, or if you prefer it in milliliters, 260 milliliters of HCl solution. And that's it for this screencast.